Fresh. I am flabbergasted. No? It is very surprising. Can you imagine yourself? No?
Flabbergasted is equal to nosebleed.
Flabbergasted is equal to nosebleed. No? Don't we love nosebleeds? No? Again, an equation that seems so alien is actually related to things that we see every day. So if you forget that it is so familiar, try to recover that sense of wonder that we want to stimulate in all our students. Then you will feel as Trudeau felt, and as many mathematicians and many philosophers felt when they first saw the Theorem of Pythagoras. It is a wonderful statement, because it is so true, especially when you look at the logic of it, it is so true. And yet it is so powerful that everything we see around us owes a lot to the Theorem of Pythagoras. We measure distances using Pythagoras. Do you know how to measure distances? You know how to measure distances?
From 2 points, yes.
If I give you a box, I give you the dimensions of the box. Can you measure the distance from one corner to the opposite, the diagonally opposite corner? Isn't that a very important piece of knowledge? It's a very basic engineering principle. If you have a box, okay, I want the distance from this point to that. And I will give you the sides. I call this A, I call this B, and the length I shall call C. How do we measure that?
Ito po mo to, sito. Sito ng dalawang nasa side.
I'll give you a clue. The clue is just an application of the Pythagorean theorem twice. I'll draw this diagonal. Now this diagonal, okay, I will call this big A, I will call this big C, I will call this big D, and I will call this big E. A, B, oh, asan ang C?
Okay na yun.
Okay na yan. Okay, let's call this C.
DE. Tapos ikot ito wala
This is A, this is C, this is B, and this is C. Okay, we want to measure EB, right?
Yes.
Let's write it here. EB squared. Using the Pythagorean theorem, that's
DB squared.
DB squared plus
DE squared.
DE squared. Right?
Yes. But DB squared.
But what is DB squared?
It's BC squared. BC squared.
DB squared. DB is the hypotenuse of one of those faces.
Yes.
And that is a right triangle. So, this is
CB
DC
CB
squared.
squared plus
CD squared.
CD
CD
squared.
squared
Quantity
plus DE
E.
squared, right?
Square mo lang.
And what is CB?
C
C squared.
plus B
What is
squared.
CD?
B squared.
B squared. And what is DE?
A
A squared.
A squared. No? So, using the Pythagorean theorem, now we can measure the distance between two diagonally opposite points of a shoebox. So this is EB is equal to the square root of
A squared
A squared
plus B
plus
B
B
squared
squared plus C
plus C
squared.
squared.
Dami.
That's
It's very simple. This is just a Pythagorean theorem. So as I said, the Pythagorean theorem allows us to measure distances. This is the power of the Pythagorean theorem. And I hope that from now on, every time you see a right triangle, you say, that's the Pythagorean theorem. Your name cards, Pythagorean theorem, everywhere. This is the Pythagorean theorem that can be directly seen. But all trigonometry, a lot of it is based on the Pythagorean theorem. Do you remember your formulas in trigonometry?
Yes.
Cosine squared plus sine squared is equal to 1. That's the Pythagorean theorem. Lastly, I want you to recall something from trigonometry. It's a practical problem. Suppose there is this is a body of water. This is a body of water. I want to measure the distance from this point, let's say, to this point. I want to measure. I'll call this A. I will call this B. But since this is a body of water, I cannot walk across to measure it in the usual way. And so, what do I do? I want to demonstrate why early surveyors found it necessary to develop the science of measurement, the science of triangles. What you do is to do a triangle. You cannot walk across water, but you can walk across land, and we can measure across land. So what the surveyor does is to do a line like this, do another line like this, and we'll call this C. So the distance I want to measure is C. Okay? Well, I do not know what C is, but I know what B is and A is, because these measurements can be done on land. Okay? And because I have ways of measuring angles, I will also be able to measure this angle. So think of this as a triangle. You know two sides and the included angle. What you want to know is the third side. Do you know the formula for this?
C squared.
Yes. This is actually the cosine law.
Yes.
The cosine law. It says that, yes, Alvin,
It says that C squared
C squared
is equal to A squared plus B squared minus 2AB sine cosine.
cosine.
That's
Cosine.
cosine. C.
C.
Big C or theta.
Theta.
This is the cosine law. We can measure A, because this is over land. We can measure B. We can measure AB. We can measure theta, and using your calculator or some tables, we know the value of cosine. And by performing the arithmetic here and getting the square root, you can get C. That is one practical use of the cosine law. Or if this is the top of a mountain, I want to dig a tunnel through the mountain, and I want to measure how much concrete I need. So I need the length of that. But I cannot possibly measure a tunnel before it is dug up, right? So engineers do. They do triangles. And using a combination of all these triangles and the cosine law and the sine law, they will be able to measure something which you cannot measure directly. You know? I hope you see this is a very practical application of trigonometry. But do you notice this? This is just the Pythagorean theorem. Except that in the case of the Pythagorean theorem,
There's
theta is equal to
90.
90. And cosine of 90 is
A 0.
0. You know? So when you have your triangle is this, C, A, B. This is 90. This is 90. You know? C squared is equal to A squared plus B squared minus 2 times AB times 0.
0.
This is, in fact, as I said, much of trigonometry is based on the Pythagorean theorem. And there are a lot of areas of calculus that are based on our ability to take distances, all based on the Pythagorean theorem. So there is a reason why that writer called the Pythagorean theorem the basis of our civilization. Many of our structures are built using ideas that came from the Pythagorean theorem. This is the cover of the January 2009 issue of the College Mathematics Journal. This is a representation of the Pythagorean theorem. 3 dots here. Here we have 5 dots, and this is 4 dots. Now my question is, what is wrong with this picture of the Pythagorean theorem? As I said, sometimes the things we see play tricks on us, even if it is published in a book or a journal. Yes, Alvin.
First, we don't measure the points, but rather we should measure the spaces in between.
That's correct. No? When we talk of the Pythagorean theorem, we are talking about lengths of the sides of a triangle. If you look at this, this is of length 2. This is of length 4. This is of length 3. No? 2 squared plus 3 squared is not 4 squared.
So it's not right angle.
So this is not a right triangle. No. I don't know whether the editors of the College Mathematics Journal noticed this mistake. No. But at least you, I hope, having gone through this class, know that something is wrong here. But it's a nice representation anyway. You know? Because here you see 3 squared, 4 squared, 5 squared, 25. I hope that you have enjoyed the Pythagorean theorem. This is a very familiar topic, very familiar equation, but I hope that my short lecture has given you new perspectives on the Pythagorean theorem. Okay, that's all, class. I hope now you see the Pythagorean theorem with new eyes, you know, and new perspectives, and that you're happier every time you look at the Pythagorean theorem. I think Alvin is very happy. So thank you very much for listening, and I hope you enjoyed the class.
Thank you, sir.